Hello, my name is Ajua and thank you for joining us as we dive into the fascinating science of soap. We're going to learn how soap molecules interact with dirt and grease, the chemistry behind a term called saponification, and why soap is essential for cleanliness. Okay, I know we pretty much take for granted that soap will keep us clean. It will keep our clothes clean and our houses clean and sanitary. But do we know how? In this presentation, we're going to look at the science of soaps. But in order to do that, we first have to look at a few basic terms in chemical properties. We need to clarify the idea of solubility, miscibility, esterification, and saponification. Yeah, those are really big words, but it's not that deep. Solubility is a term you've heard of before because it's in general use, but it is often used to describe the ability of a solid solute to dissolve in a liquid solvent. An example, a solid solute like salt in water. Miscibility is not so common a term and is specifically used to refer to a liquid solute, its ability to dissolve in another liquid solvent, such as ethanol in water. For example, alcohol in a mixed drink mixes completely and homogeneously with water, and therefore it is considered completely miscible. Oil, on the other hand, completely separates when mixed with water and are considered immiscible. The science behind solubility and miscibility, whether something will dissolve or not dissolve, is based on the atomic level or molecular structures of water, salts, and fat. And we're going to look at it right now. We all know the chemical formula of water is H2O, meaning we have two hydrogens that are attached to a single oxygen atom. But this is not a linear molecule. Remember, oxygen, well, you may remember or not, oxygen has 6 valence electrons in its outer orbit, with 2 that are paired and 2 that are unpaired. The 2 unpaired electrons can participate in chemical bonding. So to complete its outer orbit, 2 more electrons are necessary to achieve its normal configuration of 8 orbiting electrons. Hydrogen has a single orbiting electron and it's in its lone S shell and needs 1 more to obtain its noble status of 2 orbiting electrons, its happy state. Alternatively, hydrogen is sometimes willing to be more metal-like and just give up its single electron, completely emptying its single S shell. So when hydrogen and oxygen comes together in a water bond, this is sort of a hybridization of these two states. First of all, the 3 atoms form an angle of 104.5 degrees, with the hydrogen atoms asymmetrically positioned on one side of the molecule. With this configuration, we can see that the 2 paired, unshared electrons of oxygen predominantly occupy one pole of the molecule. Since electrons are negatively charged, this side of a water molecule is slightly negative. In addition, the hydrogens asymmetrically share their single electrons more with the electrophilic oxygen atom and less with themselves. Since hydrogen has only 1 positive proton surrounded by 1 single orbiting electron, this asymmetric electron sharing causes this side of the water molecule to be slightly positive. With a positive charge on one side and a negative charge on the other, water is known as a polar molecule. This characteristic is important because only polar or charged molecules dissolve in water. Non-polar molecules cannot. As an example, we know sodium chloride, table salt, dissolves readily in a glass of water, especially if the water is warm. Sodium is a metal in the first column of the periodic table, and chlorine is a non-metal on the far right side of the periodic table. Sodium, like hydrogen, has a single valence electron in its S shell, and also like hydrogen, either wants to get another electron to complete the shell or, like the true metal it is, give up its electron and completely empty its shell. Chlorine, on the other hand, has 7 orbiting valence electrons and desperately wants one more to complete its p shell. We say desperately want, but really it doesn't want anything. It's just its electromagnetic force around it means that it's more likely to attract an electron than to, say, give up an electron. With sodium's electromagnetic force wanting it to give up its single electron, the imbalance of charges makes a sodium atom slightly positive. Likewise, with chlorine's willingness or tendency to accept an extra electron, rather than give it up, the balance of charges makes this atom slightly negative, and the bond between the two is referred to as ionic. Not to be confused with the term ironic, of course. In the polar environment of H2O, or water, the oxygen or negative side of the water molecule is attracted to the positively charged sodium ion, and multiple molecules can strip it away from the lattice of the salt crystal. Likewise, the hydrogen or positive side of the polar water molecule is attracted to the negative chlorine ion, surrounding and stripping it away, effectively dissolving the solid into the aqueous environment of the water solvent. Again, how is water able to do so efficiently? Well, the electromagnetic forces, including the forces of attraction and repulsion between the charged particles of atoms, are many orders of magnitude stronger than gravitational forces. And I think we're all aware of how strong gravity is, unless you're watching this from outer space. Okay, so we've covered water, we've covered salt. Let's now look at the third factor that influences solubility and miscibility, and that is fats. Fatty acids are energy-storing hydrocarbon chains, starting with a carboxyl group at what is called the alpha end, connected to a series of hydrocarbon molecules until you get to the last hydrocarbon, always referred to as the omega end of the molecule. So in these molecules, the carbon and hydrogen atoms equally share their orbiting electrons, and therefore the tail is non-ionic and non-polar. Also known as hydrophobic, which is water-fearing, and lipophilic, which is fat-loving. In other words, this part of the molecule is immiscible in water, which is polar, but it's completely miscible with other fats. So the water molecule avoids the non-polar tail, but other fatty substances mix freely with the hydrocarbon chain. Now let's look at the carboxyl or alpha side of the molecule. This part of the molecule is an acid, and as such, the hydrogen atom on the hydroxyl group is willing to donate its shared electron to its oxygen neighbor, leaving a net negative charge on the carboxylate molecule. With its net charge, this side of the free fatty acid is miscible with the polar water molecules, or is hydrophilic. So the free fatty acid has a hydrophilic head and a lipophilic tail, and therefore can be attracted to both fat and water. This is an example of an amphiphilic molecule, from the Greek amphi, meaning both, and philia, or love. Normally, fats are stored in plants and animals attached to a 3-carbon alcohol called glycerol. If you're working in the lab, I'm sure you've used glycerol before, or maybe glycerine is commonly sold in the shops. Acids combine with alcohols through an esterification reaction. Specifically, 3 fatty acids attach to each of the carbons in the backbone, producing 3 water molecules and a triglyceride. This esterified triglyceride molecule is completely nonpolar and therefore immiscible in water, but completely dissolves in other oils. In saponification, fats in the form of triglycerides are heated with a strong base such as sodium hydroxide. During saponification, 3 sodium hydroxide molecules combine with the triglyceride, replacing the glycerol alcohol backbone and producing 3 fatty acid salts or soap. Again, in metal salts like sodium chloride, sodium is willing to give up its lone valence electron to its electrophilic neighbor chlorine, making sodium slightly positive and chlorine slightly negative. This produces a type of bond that is referred to as ionic between the 2 elements. With each atom possessing a charge, they are soluble in the polar environment of the water molecule. Likewise, sodium in the fatty acid salt is willing to give up its valence electron to the carboxylate head, making the beginning part of the fatty acid negatively charged and therefore miscible in water. The nonpolar hydrocarbon tail, on the other hand, is attracted to fatty molecules like grease and grime that may be on our dishes, clothes, or skin. The amphiphilic fatty acid salt lifts these greasy compounds from the surface, which are then carried away by the polar alpha head, which is miscible in the flowing water of the tap or shower. Finally, just a technicality here, it's important to understand that unless a specific antibiotic compound is added to the soap mixture, natural soap does not kill the bacteria on your skin surface, but simply removes the grease and grime where these bacteria live, carrying the organism away with the debris. It does, however, destroy viruses because the phospholipid structure of viruses are dissolved in the soap and effectively destroyed. Just a tip here if you're going to go make your own soap. In the making of soap, rainwater has historically been used because it is naturally soft, meaning it contains fewer minerals such as calcium and magnesium compared to hard water. These minerals can interfere with the saponification process, making it more difficult for fats and oils to react with lye to form soap. Using rainwater ensures a more efficient and effective saponification process. So we've realized that soap, because of its amphiphilic nature, can allow us to have an interaction with oil and water. What other molecules do we know of that are amphiphilic? Phospholipids found in cell membranes, they have hydrophilic phosphate heads and hydrophobic fatty acid tails. Detergents. These are synthetic amphiphilic molecules used for cleaning purposes, and they are similar in structure to soap. Bile salts. These are produced in the liver, and these molecules aid in the digestion of fats by emulsifying them. Surfactants. These are used in a variety of products, especially shampoos and conditioners, to reduce surface tension and allow for better mixing of oils and water.